Okay, so in this question, we've got two positive charges, so I'll just write it down here. Okay, of the same magnitude of charge, so let's say Q plus Q1 plus Q. They're separated by a distance D, so that would be the length of the dotted line here. Consider point A, which is a distance of 0.20D above the midpoint, and point B, which is 0.55D below the midpoint. Is the magnitude of the net electric field at point A greater than, less than, or equal to the magnitude of the net electric field at point B? Okay, so this one's a pretty challenging question. It's sort of been, to give you some insight in a sense, well, maybe if I talk about the question without, of course, knowing the answer, you may be inclined to say that A might be greater than, because it's got a sort of it's closer to each of the charges than B is, for instance, and we know there's a relationship between the field and the distance, an inverse proportionality to the square of the distance. But in choice A, there's going to be, in a sense, going to be large x components and small y components. And the x components are going to cancel in both cases. So I really have to ask myself the question, is the sum of the y components at point A due to both fields greater or less than or equal to the sum of the y components for B? Now B would have, in a sense, a greater amount of the field in the y direction, but it's slightly further away. So these distances have been chosen that it's not just going to be a simple sort of a guess. So we really have to work out the math and the trig to figure exactly what the answer is. So okay, let's start with adding some information to the diagram here. So I know this distance here, technically if you want to go to the center of the charge, this is the distance of half d, or d over 2, because they're separated by, the charges are separated by a distance d. So the field, and let's say point A, I'm trying to draw this reasonably accurately. So it's along the line connecting the two charges, and I'll make this maybe a point. Make it this big. And what we really need to, in order to find the size of the charge, we're going to have to find what is the distance between the charge on point A and then this one over here. We'll exert a field, again pointing away from this charge, and we're looking for the sum of these two fields. So maybe if I call this the left and this is the right, this would be E due to the left charge, this would be E due to the right charge at point A, again pointing away from the positive charge, and we're looking for the sum. And because of the symmetry in the problem, the charges are the same magnitude, they're equidistant from point A, they'll exert the same magnitude of the field at point A, so their x components will be identical in opposite direction, so they cancel. So really the net field of A is the sum of the y components of these fields. So let's focus in on point A. So what I want to know is, what is this distance? I'll call this distance or A. Okay, so we can use Pythagorean theorem. So the distance or A is going to be the square root of 0.2d all to be squared, so this height, plus 0.5d, or d over 2, all to be squared. So you can use the Pythagorean theorem to figure out what that distance is. And that works out to be 0.53854.54d. So I encourage you to keep a few extra sig figs when you're looking at your calculations, which I'll do in Excel. Okay. So now we can figure out that I know that the E left, which has the same magnitude as E right, is going to be K times Q divided by 0.54d all to be squared. So that would be the size of one of these red arrows in terms of the given quantities. Zoom in here. Okay. Now what I need to do is find the y component. So what I mean, so if I think about, I need to know this angle here, which will be the exact same as this angle up here. So the y components will be the size of that e times the sine of that angle. We're looking for the opposite side. So the net field at A is ELY plus E right y, which is basically just 2 times E in the y direction. If I just call these are both the same size, they're both equivalent to this amount. So it will be 2 times KQ divided by 0.554 D all to be squared times the sine of theta. So I'm trying to find the y components. Now the theta will be given as a tan inverse of 0.2 over 0.5d. So, or you could also use now that you have the hypotenuse, you could also use one of the other trig functions, but since I know these exactly, these are 0.2 and 0.5, I'll use a tan. So the E net at point A, I'm going to take all this stuff out here. I'm going to put the 2 out. I'm going to do the sine the sine of the tan inverse of 0.2d over 0.5d. I believe that works out to be 21.8 degrees. And then I'm going to divide this by, I'm going to take out the 0.4 squared, 0.54 all to be squared, and then times KQ divided by D squared, because this is our known quantity. Sorry, it looks quite complicated, but what you're doing here is this angle here works out to be, if you just want to do that separately, I believe it's 21.8 degrees. You can take the sine of that angle here, then multiply by 2, then divide it by the 0.54 squared, and then keep your KQ over D squared. So if you do this correctly, I believe this works out to be 2.56. Or 2.6 KQ over D squared. So I picked the values to be pretty close, or 2.6 KQ over D squared. And that gives us the value of the electric field at point A, or 2.6. Yeah, so 2.6 KQ over D squared. So we do the same process for B as we've just done for A. The only thing that's changed here is that we're finding our B, instead of 0.2 we have 0.55, but I think that's everything else is going to be the same. So I'm going to switch the color here. So the distance for our B, that would be sort of looking at this distance here in a ways. What's the value of our B? And so we obviously a little bit bigger. So we're going to do a Pythagorean theorem again of 0.55 d all to be squared plus 0.5 d all to be squared, and that works out to be 0.74 d squared. Okay. And then again we're going to do our summing of the y components. So again, in this particular case, I'll repeat what I have here, because it's going to be the same thing. So I'm going to get an E net at B is going to be E left plus E right, and only with the y components, which again will be 2KQ divided by the 0.74 D all to be squared times the sine of the angle, where the angle in this case is the tan inverse of 0.55 D over 0.5 D, and that angle In the second case, I think it's 47.7 degrees. So here, if this is the field here, you're looking for the angle here, theta, this works out to be, I believe, 47.7 degrees. So to get the E net at B, then we're going to do 2kq over 0.74 d all to b squared times the sine of that angle. So I'm going to do the same calculation I have here. So it's 2 times the sine of the tan inverse of 0.55d over 0.5d, and all divided by 0.74, and all to be squared times kq over d squared, and I believe this works out to be 2.68 or 2.7 kq over d squared. So I just picked the values of the distances, so that wouldn't be obvious, hopefully, which is the right answer, and I just picked them enough that the point is actually closer, and actually ends up having a weaker field due to the addition of just the angles and angles I picked. That even though A is closer, it's disadvantaged by a smaller angle and the larger x components and smaller y components than the 0.55d for B. It just so happens to work out that it's just slightly larger at point B for these distances chosen, due to the vector superposition, not the algebraic summing of the fields. So A is slightly less than, but by a very small margin.